There is a machine drifting through the darkness between stars right now. It was built by human hands in the 1970s. It has a computer weaker than the calculator in your pocket. Its power source is dying, losing exactly 4 watts every single year. And nobody can go out there to fix it. It is more than 15 billion miles from Earth. And the signal it sends back home, the whisper that crosses that impossible distance, travels for 23 hours before anyone on this planet even receives it. This is not science fiction. This is Voyager 1, and its final chapter has already begun. Nobody told you the whole story. That is the first thing you need to understand before anything else in this video makes sense. The version you heard, the one where a spacecraft was launched, flew past some planets, took some pictures, and disappeared into space. That version is technically accurate, but it leaves out everything that actually matters. It leaves out the desperation, the human stubbornness, the last-second decisions, the slow erosion of a dying machine, and the question that nobody at NASA has been able to fully answer yet. When the final signal from Voyager 1 goes dark sometime in the 2030s, what exactly will humanity have lost? To understand what is happening right now in the summer of 2026, you have to go back to the beginning. Not because the beginning is poetic, though it is, but because the beginning is the only way to measure just how staggering the ending truly is. On September 5, 1977, a spacecraft approximately the size of a small car was launched from Cape Canaveral, Florida. It was mounted on a Titan Centaur rocket and pointed toward the outer solar system. The original mission mandate was 5 years, 5 years of data, 5 years of planetary flybys, and then the mission would be considered complete. The engineers who built it, the scientists who designed its instruments, and the administrators who approved the budget were thinking in terms of a 5-year project. Nobody, not one person in that room, was thinking about what this machine might still be doing 49 years later. But here is where the first layer peels back. Voyager 1 was not built for the journey it actually ended up taking. It was built for Jupiter and Saturn. That was the assignment. Fly past Jupiter, collect data about the gas giant and its moons, continue to Saturn, document the rings, and wrap up. The spacecraft did exactly that. It swept past Jupiter in March 1979, revealing volcanic activity on the moon Io that no telescope on Earth had ever detected. It photographed the swirling storm systems of the gas giant with a clarity that rewrote entire textbooks. Then it reached Saturn in November 1980, delivering the closest and most detailed images of Saturn's ring system that humanity had ever possessed. And then, technically, the primary mission was over. Voyager 1 had done what it was sent to do. Think about what that means. The mission was complete in 1980. Everything that has happened since then, every discovery, every data point, every instrument reading sent across the void, has been bonus material, extended mission. But the word extended does not begin to capture 45 more years of continuous operation. That is not an extension. That is an entirely different story being written by a machine that was never designed to write it. What happened next is the part that most coverage skips, because it does not fit neatly into a single headline. After the Saturn flyby, Voyager 1's cameras were still operational. The spacecraft was racing outward into the deep solar system, accelerating away from the sun at a speed of about 38,000 miles per hour. Mission planners began discussing what to do with those cameras, instruments that were still functional but had no planned targets ahead. And this is where a single scientist changed everything. Carl Sagan, who was part of the Voyager imaging team, had been carrying an idea since 1980. He believed that before the cameras were powered off forever, Voyager 1 should turn around and take one last photograph. Not of a planet it had never visited, not of a distant nebula. He wanted the spacecraft to photograph home. He wanted a picture of Earth from the edge of the solar system. And almost nobody at NASA agreed with him. There were real technical objections. Pointing the camera so close to the direction of the sun risked damaging the imaging system permanently. There were resource objections. There were scheduling objections. For nearly a decade, the idea sat in limbo while Voyager 1 continued its outward journey. It took until 1989, 9 years after Sagan first proposed it, for NASA to finally approve the photograph. And even then, it only happened because the NASA administrator at the time, Richard Truly, personally intervened to make sure it got done before the cameras went dark. On February 14, 1990, the command was sent. Voyager 1 warmed up its cameras and began photographing the solar system for the last time. It captured 6 planets: Neptune, Uranus, Saturn, Jupiter, Earth, and Venus. Mercury and Mars were lost in the sun's glare. The entire sequence was 60 images. But among those 60 images was one frame that would become arguably the most philosophically significant photograph ever taken. The camera pointed in the direction of Earth, and from a distance of 3.7 billion miles, Earth appeared as a pale blue, suspended in a scattered ray of reflected sunlight. The planet that contains every human being who has ever lived, every civilization ever built, every war ever fought, every piece of music ever composed, every act of love and cruelty and genius in the entire recorded span of human history. All of it occupied exactly 0.12 of a single pixel in the camera's frame. Not even one full pixel, a fraction of one pixel. And 34 minutes after that image was captured, Voyager 1 powered off its cameras forever. That is the detail that makes the stomach drop. Not the image itself, though the image is extraordinary, but the timing. The entire sequence of 60 photographs, including the pale blue dot, was completed in the very last window before the cameras were shut off for good. If Carl Sagan had not spent 9 years fighting for that photograph, if Richard Truly had not intervened at the final moment, and if the command had arrived 35 minutes later, those cameras would have gone dark without ever looking back. The most famous image in the history of space exploration was 34 minutes away from never existing. But here is where it gets worse. Or, more specifically, here is where the real story of 2026 begins. Because the cameras shutting off was not the end of Voyager 1. It was barely the middle. After the cameras went dark in February 1990, Voyager 1 kept going. It kept transmitting data. Its other instruments, 10 sets in total, measuring everything from cosmic rays to plasma waves to magnetic fields, continued operating as the spacecraft pushed deeper into the outer solar system and, eventually, beyond it entirely. In August 2012, Voyager 1 crossed the heliopause, the boundary where the sun's magnetic field and charged particles give way to the conditions of interstellar space. It became the first human-made object in history to leave the solar system, the entire sun-governed bubble of space that contains every planet, every moon, every asteroid, every comet humanity has ever observed. Voyager 1 crossed out of all of it, and it was still transmitting data. What most people are not seeing is just how unprecedented that science truly is. Voyager 1 is the only operational spacecraft that exists in interstellar space. Not one of two, not one of several, it is the only one. Along with its twin Voyager 2, which crossed the heliopause in 2018 on a different trajectory, these two machines provide the only direct, in-place measurements of the space between star systems. Not telescope observations, not mathematical models, actual direct readings from instruments physically present in interstellar space. There is no satellite replacement waiting in orbit. There is no follow-up mission already en route. There is no backup. When these machines go silent, that window of direct measurement closes, possibly for decades. And the window is closing. This is what happened this year in 2026. And this is what you need to understand about where Voyager 1 stands right now. The spacecraft runs on a radioisotope thermoelectric generator, a device that converts heat from decaying plutonium into electricity. It produces no solar power. It cannot be recharged. The plutonium that powers it has been slowly decaying since 1977. And that decay costs the mission approximately 4 watts of electricity every year. For what sounds trivial. On Earth, 4 watts is a nightlight. On Voyager 1, 4 watts is the difference between a science instrument continuing to operate and a science instrument going permanently dark. The shutdown plan has been years in the making. NASA did not arrive at this moment unprepared. The Voyager science and engineering teams sat down together long before the crisis arrived and agreed on the precise order in which instruments would be powered off, a deliberate triage designed to preserve the most scientifically valuable capabilities for as long as possible. Of the 10 instrument sets that each Voyager launched with, 7 have already been shut down. 7. What remains on Voyager 1 as of July 2026 are 2 science instruments: the magnetometer, which measures the magnetic field around the spacecraft, and the plasma wave subsystem, which detects plasma oscillations and helps scientists map the density and behavior of the ionized gas through which Voyager travels. Everything else is gone. The cameras were first powered off in February 1990. The planetary instruments, the ultraviolet spectrometer, the infrared instrument, all switched off in the years that followed. The cosmic ray subsystem was shut down on February 25, 2025. And most recently, On April 17, 2026, NASA sent a command that took 23 hours to reach the spacecraft. The command deactivated Voyager 1's low-energy charged particles experiment, the LECP, an instrument that had been operating almost continuously since the day of launch in 1977. The LECP had measured ions, electrons, and cosmic rays from both the solar system and the galaxy beyond it for nearly 49 years without interruption. When that shutdown command executed, the LECP went dark. Read that again. An instrument that operated for 49 years just went offline permanently. Not because it failed, not because something broke, but because there are now so few watts available that keeping it alive would threaten the survival of the instruments that remain. According to Kareem Baradin, the Voyager mission manager at NASA's Jet Propulsion Laboratory, the decision was made after a routine roll maneuver in late February 2026 caused a power level drop that nearly triggered the spacecraft's undervoltage fault protection system, the system designed to shut everything down and put Voyager into a protective safe mode. They came within a fraction of losing control of the spacecraft entirely. The LECP was shut off to pull the mission back from that edge. And this is where everything changes, because what is left now is not a failing spacecraft stumbling toward silence. What is left is a deliberately engineered survival. Two instruments remain, and both of them are among the most scientifically critical tools Voyager could possess for the environment it currently occupies. The magnetometer is reading magnetic field conditions in interstellar space, data no other operating instrument anywhere can replicate. But the engineers are not simply watching the power drain away. There is a plan, an aggressive, high-risk plan that the Voyager team has unofficially nicknamed the Big Bang, a coordinated overhaul of the spacecraft's powered components, swapping several systems simultaneously for lower power alternatives in one compressed operation. If it works, it could free up enough electricity not just to extend the mission's operational life, but potentially, and this is the part that still sounds almost impossible, to restart the LECP instrument that was just shut off. The Big Bang is being tested on Voyager 2 first, which has slightly more power to spare and is marginally closer to Earth, making it the safer test subject. Tests were scheduled for May and June of 2026. If those tests succeed, NASA intends to attempt the same procedure on Voyager 1 no sooner than July of this year. The outcome is not guaranteed. Nothing about this mission has ever been guaranteed. Meanwhile, Voyager 1 continues to move. It is currently about 15.8 billion miles from Earth, 25 billion kilometers. And that distance grows by approximately 38,000 miles every hour. On November 18, 2026, it will reach a milestone that no human artifact has ever crossed. It will be exactly one light day from Earth. That means the electromagnetic signal Voyager 1 transmits, a signal so faint it arrives at Earth weaker than the power of a refrigerator light bulb, will take a full 24 hours, traveling at the speed of light, before it reaches the deep space network antennas waiting to receive it. One day of travel at 186,000 miles per second, just to cover the distance from a machine humanity launched to the planet that built it. The antennas themselves are part of a story that does not get enough attention. The Deep Space Station 43 in Canberra, Australia, is the only ground antenna on Earth capable of sending commands to both Voyager 1 and Voyager 2. There is no other station with that capability. Between May 2025 and February 2026, that antenna was offline for major structural upgrades, with only limited operational windows available in August and December 2025. For the better part of 9 months, the ability to send new commands to the most distant spacecraft humanity has ever built was severely restricted. The fragility of the chain connecting Earth to Voyager is easy to overlook, until you realize that a single antenna upgrade schedule can determine whether engineers can intervene in a crisis or simply watch it unfold. There's another dimension to this story that rarely surfaces in mainstream coverage. Attached to the outside of Voyager 1, and its twin Voyager 2, is a gold-plated copper disc, 12 inches across, carrying 115 photographs, a range of scientific diagrams, audio recordings of music from across human cultures, nature sounds, and greetings recorded in 55 human languages. This is the golden record, curated by Carl Sagan and his team. It was designed not for any audience that exists today, but for whatever intelligence might intercept the spacecraft tens of thousands of years from now. In approximately 40,000 years, a figure that is not a guess, but an astronomically calculated trajectory, Voyager 1 will come within 1.7 light-years of a small, obscure star in the constellation Ursa Minor. Whether anything is there to receive the disk is unknown. Whether the disk will survive that journey in a readable condition is uncertain. But it was launched anyway, because Carl Sagan believed that the act of sending a message mattered even without the certainty of a recipient. The spacecraft that will carry that record into deep time is currently operating on 2 instruments and an engineering transmitter, powered by the radioactive decay of plutonium loaded onto the vehicle 49 years ago. This is not chaos. This is the endpoint of extraordinary longevity, meeting the inexorable mathematics of power loss. What makes the current moment different from every previous moment in Voyager 1's long history is finality. For decades, each shutdown could be framed as a trade-off. Lose one instrument, gain time for others. But the instrument inventory is now so thin that each shutdown from here forward is not a trade. Each one is a subtraction with no replacement. When the magnetometer eventually goes dark, there will be no remaining instrument to cover what it was measuring. When the plasma wave subsystem stops transmitting, the acoustic picture of interstellar space that only Voyager 1 could paint goes permanently silent. The engineers at JPL say they hope to keep at least one science instrument operational on each Voyager into the 2030s. But they also say, and this part is important, that unforeseen problems could shorten that timeline at any moment. An unexpected thruster failure, an electronics fault in a computer that runs 8,000 instructions per second in an environment where no repair mission can ever reach, a power drop that triggers fault protection before any command from Earth has time to intervene. Once an instrument shuts off permanently on Voyager 1, the heaters that kept its electronics above catastrophic temperature limits shut off, too. In the absolute cold of interstellar space, the components freeze. They do not fail dramatically. They simply become inert. There is no restart procedure. There's no recovery. The hardware that made measurements no other probe could replicate sits frozen and silent, traveling outward at 38,000 miles per hour into a darkness where it will drift for longer than recorded human civilization has existed. The signal that comes back from Voyager 1 now is already a ghost of what it once was. A transmitter that outputs roughly 22 watts, less power than a standard light bulb, firing information across 15 billion miles of space. By the time that signal arrives at the Deep Space Network antennas, its power has spread across a sphere so vast that the energy reaching the receiving dish is measured in fractions of a trillionth of a watt. Engineers have to filter it out of background noise with some of the most sensitive radio receivers ever constructed. That is what is being maintained. That is what the shutdowns of instruments are buying time for. The continuation of that whisper for a few more years from a place that nothing else humanity has ever built has managed to reach. Former Voyager project manager John Cassini put it plainly in a 2024 NASA statement. We didn't design them to last 30 years or 40 years. We designed them not to fail. Nearly 50 years in, the design is still holding, but the physics is winning. The plutonium will keep decaying. The 4-watt annual loss will keep accumulating. The decision tree that engineers have followed for years, which instrument to sacrifice next, which system to protect a little longer, will eventually reach its final branch. When that last instrument finally powers down, Voyager 1 will not immediately cease to exist. The transmitter and onboard computers may continue operating for some additional time, sending back engineering data, the spacecraft equivalent of a pulse with nothing left to say scientifically. The Deep Space Network will keep listening. Eventually, that signal too will fall below the threshold of detectability, or the power will drop below the minimum required to maintain transmission. And then there will be silence. Not the silence of failure, the silence of completion. Of a machine that was asked to operate for 5 years and instead spent nearly half a century doing science in places no human instrument had ever been. That survived computer failures and thruster degradation and power crises and the cold mathematics of radioactive decay. And then finally, quietly ran out of the last few watts it needed to keep speaking. What does that mean for humanity? The real story here is not the spacecraft. The real story is what we will lose when it goes quiet, and what that loss reveals about where we stand in relation to the universe around us. Right now, in the summer of 2026, the 2 Voyager probes represent the only direct sensing capability humanity possesses beyond the edge of the solar system. No mission is currently en route to replace them. No probe is scheduled to reach interstellar space within the next 20 to 30 years. The data the magnetometer and plasma wave subsystem are sending back, live readings from actual interstellar space in real time, from instruments physically immersed in that environment, will not be available again from a new spacecraft for a generation or more. And so every day that those two remaining instruments keep transmitting is genuinely irreplaceable. Every reading is a measurement that cannot be taken again, because the machine taking it is sliding further into a void it cannot return from. Somewhere beyond 15 billion miles of darkness, a small golden record is attached to the outside of a dying spacecraft. It carries photographs of a sunrise, of a nursing mother, of the UN building at night. Images that Carl Sagan and his colleagues selected as representative of what humanity is. It carries music. It carries the sounds of wind and rain and thunder and ocean surf. It carries greetings in 55 languages. In 40,000 years, it might pass close enough to a star that something could theoretically find it. But long before that happens, perhaps in a few years, perhaps by the end of this decade, the spacecraft carrying it will stop transmitting. The instruments will go dark one by one. The signal will fade. And what was once the most distant conversation humanity had ever maintained will simply end. The question that lingers, the one NASA cannot fully answer, the one the engineers at JPL live with every day they sit down to manage those final few watts, is whether the ending represents an achievement or a warning. Is Voyager 1 proof that human engineering can outlast its own expectations by an order of magnitude? Or is it a reminder that in a universe of this scale, even our most extraordinary reach, 15 billion miles, 49 years of continuous operation, the boundary of interstellar space itself, amounts to less than a single step on an infinite road? The Big Bang fix is being tested right now. The magnetometer is still reading. The plasma wave subsystem is still listening. The signal is still arriving at Earth after its 23-hour journey across the void. But the power is still dropping, 4 watts every year, without exception, without pause, without the possibility of reversal. And somewhere in that arithmetic is the answer to a question nobody wants to ask out loud. How much time does humanity's furthest outpost actually have left? The mission managers hope for the 2030s. The physics will have the final word. And when that final word comes, it will arrive not as a dramatic announcement, but as silence.